Hi, everyone. First time experiment as always. Hope it goes well. Today we're not really talking about any particular questions per se, but we're designing and discussing the paradigm, the concept, the idea that usually goes under the name reactive streaming, which is asynchronous, event-driven, actor-reactor, replayable, persistent, client-server, or whatnot. We have a bunch of architects here who use it from different sites, be it client-side, server-side, middleware, gateways. And Victor is kind enough to tell us more about his experience researching this guy. So we had a small chat beforehand, off the record. Let's maybe start by outlining whether it's necessary. What are you supposed to use it for? What it is not suited for, and how it emerges, how it evolves.
Hi. So my name is Victor. I work as an architect at Stars Technologies, representing PokerStars. Like many programmers, it's a bit of a journey to get into reactive streaming and starting to think that way. Like most people, you first learn functions, and you learn about state, and you learn about local scope, and you're kind of used to thinking of your programs in a kind of model of like to it and maybe where to save something, and you kind of start to think about your systems like in a kind of RPC sort of way, like someone calls this function remotely, it does something, modifies some internal state, then someone calls another function, and you kind of stitch it all together with a kind of pattern that you've been taught about object-oriented design, trying to break things down, manage them with functions, and that's kind of how folks write applications a lot of the time. And then you kind of get into this functional paradigm, like, oh well, really this state is just an object, and we can map on top of it, we can reduce it, we can do things to it without having to go inside and fiddle with the bits. We can call some generic functions to transform the state and output a new state. And then I guess you really start to think, and you realize that, hey, no, everything is just a stream of changes to this state over time. And all your operations that you're doing can really be broken down as transforms on this stream to produce some desired output, whether that's transforms, merging two streams, being client, like a user's interaction stream, and a server's data stream, merging those streams and producing a user interface. And everything you really start to think of as a source of a data stream and how that can be combined with other data streams to produce whatever it is your application is supposed to be producing. And that kind of, I guess you could say, evolution of perspective is something I've seen a lot of my colleagues as well go through. And, it takes a while to sink in. But when it does, I really think that you can, the goal of all this is, why do we do all this? I guess it's because we can write often 10 lines of code where otherwise you would have written 200. And it makes everything a bit easier to conceptualize and to understand and to read and maintain.
So when you say application, user interface, I think what you mostly have in mind is React, Redux, the browser, the DOM tree, right?
Yes and no. Yes and no. I mean, that's definitely the world I'm most comfortable in. But I've seen this pattern very successfully applied on servers, on APIs, on all kinds of server-side problems that needed to take some kind of real-time data stream or near real-time or continually evolving and transform it into something else, which is usually the goal of most API gateways, right? Take a stream of operations on the database and transform that into a real-time view of the data whenever it's called.
All right, let's decompose it from the beginning. Imagine you just have an API which has a bunch of synchronous calls, HTTP GETs, posts, RPCs, gRPCs, or whatnot. At some point, you realize your application is a lot more asynchronous. So instead of just expecting response synchronously, you use some kind of fire and forget with request ID, and then eventually you get a response with certain request ID, maybe in arbitrary order, maybe it's lost in transit or whatnot. For all these, you don't need any extra tooling. You just change the format of your JSONs, right? So it just sounds to me, and I guess many people will agree, that reactive streaming is an emergent property. It's not that your application design suddenly becomes reactive streaming aware. It's a gradual process. It's a gradual path. So what do you think are some milestones on this path?
I guess I wouldn't say it's your application. It's more that your own mind kind of becomes more reactive streaming aware, and as it is, your application design tends to follow it. But I guess milestones on the path would be, instead of your application itself making an outgoing RPC call to do something, you would be looking for a push stream of changes, of notifications. Like, instead of constantly going to, let's say, Mongo and reading something out, you would be tailing the op log, and you would be proactively ingesting and proactively transforming that kind of thing. So it's whenever you start wanting to be pushed information instead of looking to call out and get something or pull or any of those mechanisms, I think that's a major milestone.
Okay, so there are a couple of ways to go from here. Let's start with the simple ones. Imagine you want to drink the Kool-Aid, or maybe not you, maybe someone else who's considering changing projects or whatnot, and they hear that on the project they are really looking into joining. You hear they use Kafka as the data bus, and they use RSocket between backend and front end and gateways and middle tiers and whatnot. This may or may not be reactive streaming, right? It could be a bunch of kids who just learned these words, Kafka and RSocket, and they still write the good old synchronous code, pretending they use all these things. Or they could be really, really up to something. How would you tell? What would you ask them?
Well, I guess, even if they're a bunch of kids and they take these technologies and they read the internet on how they're supposed to be used, and they just follow the patterns, and probably they're actually going to be reactive streaming. Like any kind of just naive use of Kafka is going to lead you down to stream transforms as a cornerstone of your application. So you'd have to kind of try hard to fight it at that point if you just pick those technologies.
Okay. One thing we did mention is that once you start going all in on reactive, you can't really use synchronous calls. So you have to, like, every single internal or external component call must be synchronous. And the first question I asked you right away back then was, hey, if I have a cache. So let's say I have a module that you can think of it functionally, not in terms of functional design, but in terms of functional programming. You can think of it as a monad with some state that has been altered by external push calls. But what if you do need to use a cache?
Well, it's cache essentially seems like a side effect on a stream or an additional operation on a stream where you have an incoming data stream and you want to persist it somewhere. Well, you would just tap into that stream, persist whatever it is you need to, and kind of carry on. And then if you're trying to start up and you read the cache somehow, you would start, you would initialize your stream based on the cache value and, start from there, I guess. Yeah, everything kind of has to, for the application to not have pain, you kind of want to start to think of everything as the start of a stream or an operation on a stream. And everything just, once you can really wrap your head around like how do I take this static data and is it really a stream, and how can I make it into one? And it doesn't really even seem like a stretch. It doesn't seem like you have to jump through hoops or kind of force the pattern where, if you just start to think of like, well, my application is starting up, I need some initial state and I want to read it from some kind of cache. Well, okay, so I would start my, I guess the whole, it boils down to the fact that everyone, computer systems, people, they all perceive time as an arrow in one direction. And your stream is just your state along that arrow, what's happening to it. So if you're starting your application, it's the year zero for this application. It's just starting. So you want to start it from something. And if that happens to be a cache, okay. And then the arrow continues. So then you're applying whatever operations your application needs to do on that stream and carrying forward.
This sounds simple, but in reality, I'm trying to gently come to the hardest part of this. So if you are synchronous, if you can afford to make calls and wait for some results because you know the wait is not going to be too long, the logic kind of is straightforward. Again, you can argue that it's a feature of a human brain, but if there's a function of 3 lines, you know what to expect. And now there are 2 ways to take from here in terms of wrapping your head around that. One is instead of making synchronous calls, you can imagine every single function doesn't return a value but has a callback, which would be a callback hell. But if you use async await, you kind of syntactically the code still looks as a linear piece of logic, A followed by B followed by C. But then if every callback can come at any time, more or less, if you have multiple processes running concurrently in your state machine, then your ultimate state machine becomes a Cartesian product. So if it's three thingies of 5 states each, it explodes exponentially. So on the one hand, it sounds really cool that you just need to have your own black box, which is in one of many, many states, and every single new event pushed to that can help it travel between traverse the states graph. On the other hand, it's a huge pain to write maintainable code in this degree, in this realm. So how in practice, let's say you have some cache, and let's say you have some user logins, sessions, messages, or whatnot, timers. How do you make sure that you are drinking the Kool-Aid, you have all the benefits of reactive streaming, and you still make sure that mere mortals can maintain this code?
I guess it's maybe to answer, I'd like to first start with the simpler kind of mental transition, and the same kind of questions get asked around. If you're using long operations on, let's say, arrays, lots of map and reduce and for each and so forth, and each of those mutates the array, and each of those obviously has a performance overhead compared to a lot of for loops. And new call stacks, you have a lot of copies, you have a lot of stuff that's going on in the background. But in the end, you often end up with a lot fewer lines of map reduce code than you would of loops trying to come up with the same result from your initial data. So, but at the same time, the programmers who are maintaining this, they have to understand and think in a model of, functions that work on data and output new data in a kind of more functional model. So, how do you teach people they're exclusively used to writing, classes and for loops and have never seen map and reduce in their lives? How do you teach them to maintain this code? Well, it's a process, but I think after a while, for most people I've seen the light bulb kind of turns on, and they realize that actually, yeah, I can take this initial state and I can go through several discrete operations to come up with my result. That's all kind of static, right? It's there's no arrow of time involved there. We're just going in one code block and we're doing, some kind of series of operations on some data.
Hold on, I think you're jumping here. I hear you, but again, to to me, it was quite a revelation. I guess to most people it will be as well. That on the one hand, you can pretend you are functional. I mean, JavaScript is a functional language. It has functions as first-class citizens. It's not hard to rewrite for loops into maps and filters and reducers. On the other hand, you have true functional programming, where you have monads, where you have laziness, where you have infinite data structures. I guess for most of us here, this gap is bridged. We know once you've learned how to go from for loop to filter reduce in the JavaScript world, suddenly you understand infinite streams and how to process them. I'm not asking this. I mean, if it was so easy, everybody would speak functional programming fluently by today, because we have functional reactive ways of writing at least front-end React JavaScript code. We do use this paradigm so many years by now, but people still have trouble grasping this on the middle tier, on the backend, in terms of database access. There seems to be something to bridge. There is some huge gap to bridge. How do we get there?
I think a lot of it, how to say, a lot of the more, rigorous languages, you have to fight the type system a lot more. You have to understand how, and this is the case too, where, these days I'm writing mostly TypeScript, which has, pretty strong type system if you use it correctly, according to kind of best practices. It's definitely a little bit more optional than it is in something like Java. But even in Java these days, when they've using something like Mono, once you understand kind of how the types flow through the system, and it's the same, like, in Java, you can go on the same journey of realizing that map reduce is a thing, and how the types flow through that, and how the compiler understands all of that. And once you've gone through that journey on static data, it becomes a lot easier to go through on streams, and on realizing that you're just performing an operation with time as a factor, as opposed to just in a single thread. I'm not sure if that's.
I still think like this idea of the time arrow seems to be crucial, but in my view, in my experience, it does require some light bulb turning on. And then you have relativistic processes where multiple time arrows intersect at random places without necessarily, like, the order is respected. Everything else can go in weird ways. Look, what I'm trying to ask is, so let's say you have a simple actor model data processor. For somebody who knows how single-threaded apps work, for someone who knows how message loops work, for them, oh, it's simple. Actor model is just while get message, translate message, dispatch message. That's my actor, and the actor body is just a switch on message type. From there, they can easily make a jump to, oh, instead of the message loop in the local OS, in the local operating system, I have a Kafka receiver, and that's where the messages come from. Like, again, for most of us, I think for all of us here, it's clear that this jump is way more than halfway to actually writing distributed map reducers or distributed stream crunching. But I still feel like people have troubles grasping that. I mean, which is
like,
so.
I thought about it, and to me, it's the same jump as, for example, when you have to make in your mind from from procedural programming to functional programming, and it's close. I think like all this reactive streaming is trying to solve the complexity of managing the state, and as that's the biggest problem. And like functional programming tried, and it's like it fought hard to wrap all the side effects and try to manage them with types. And I think like in reality, the state management is either complex or doesn't fit into that paradigm. And we saw that in like traditional functional languages, because it's hard, like people struggle with it. That's why it never like really flew, because managing state is hard, and trying to like hide its complexity is hard. And like a good example of that is also like Golang is a good example. If you watched like the initial presentation from Rob Pike on effortless concurrency, and the paradigm was there, like I said, it's a message passing. It's that the model of channels. But you never find a modern Go program without mutexes, for example, that share state, even with all the channels, because like real world, it's hard to do that. And of course, with mutexes, I found multiple bugs in the very well known libraries. Like I found like a concurrency bugs in gRPC library and in a like Minio-Go library. And like I found like even in my own software, like I found multiple concurrency bugs related to the mutexes usage, but people will still use them because it is most of the like industrial professional software using mutexes in Golang. Even though like there is a paradigm on the side that's supposed to solve this problem, this effortless concurrency with channels. And I think the same with streams. It's a model that helps you, but in real world, it's too hard. In some cases, in many cases, in professional, like maybe like in most industrial usage, it will be really too hard to isolate it. And that's my take on it. That's why it's hard. I think like that's what you asked, like why it has required this like jump and like there's a barrier to adopt it. I think that's the barrier to me.
Well, it's kind of like effective usage of the Linux pipe, right? It's actually an incredibly powerful tool, and it's also very, reactive streamy in the sense that you're just taking an input data stream and you're applying a bunch of operations on it. But to actually, even in the 80s, someone who could really effectively use that and chain things together properly with it, they had to fully wrap their head around what it's doing and how it's working. And once you have that, then it becomes like sed and awk and all these tools that beginners struggle with. You can do really powerful things with very few lines of code. And I guess it depends on what audience you're writing the code for, whether the people who are helping you maintain it are people who can wrap their head around what's going on. And if not, you kind of have to simplify things down. And I do think in a lot of ways that React itself and the front end world has kind of helped people. Angular, modern Angular has also done an excellent job at being really close to RX and integrating it very well into the whole design pattern. And I think that there's a lot that we can do as architects, as system designers, to kind of make it easier for people to get started the right way, because you can kind of skip the step, honestly. If you're just beginning and all you've ever seen is reactive streaming and all you've ever known is that, then you don't really have to go down the, first solidify like classes and static members and RPC. If you can just skip that and not ever think about it and just go straight into like stream transform as a way of life, then it's easier to learn than to relearn, right?
Let me step here with an example. I was introduced to Unix pipes from the early stages, and for me it's really easy and understandable and really nice to use. But now at work, when I talk to people, I see that people are struggling with that. They don't understand the whole principle. And also, I would add that the functional programming is quite connected to a lambda calculus of a lambda charge, and our like regular command programming is mostly related to von Neumann architecture. And essentially, we have to admit that von Neumann architecture actually took the world more broadly than lambda calculus, and more people are introduced early and more often to like common ways of thinking instead of lambda calculus. That's why even though I actually from the command imperative, I believe that's actually the initial point in mind, which was seeded inside me.
I was actually hoping we will get to Unix pipes, because I think it's one of the easiest entry points into what we're discussing right now.
If only they supported if only there was a more structured format, because there's some modern tools which allow you to do more structured data format around Unix pipes, but I think the reason most people struggle with them is because you know, the unstructured nature of the data exchange, and you know, often like white space or columnar or CSV or some other kinds of things that some of the common commands output, it makes it a bit more tricky to string things together. I think, you know, in a type check language which has structured data types, that it's a lot easier to understand what each aspect of your stream, of your pipe, what it's operating on, what it's receiving, and what it's outputting. And it can be statically, you know, type checked by a reasonable compiler. So I think that's why a lot of people have a hard time with Unix pipes. You know, even myself, like it was easier for me to understand RxJS and work with it because I'm working on JSON than it is for me to construct, you know, long chains of Unix pipes, because I just lose track of, like, it's just too much to keep track of what's going on at each stage. And I guess I'm not natively, you know, I don't use the commands often enough to just know by heart what they all do.
You know,
what?
like to me, I think that's
Yeah.
the biggest difference between backend and frontend, because on frontend you have less persistent state to manage, and that's a big problem that dominates the backend development. Like Dima, you mentioned caches, and there's databases, and there's other persistent state. And if your pipe fails, you have to know how to recover from it. And I think like that complexity kind of dominates, and that's where the most effort spent. And like streaming is only like partially helping, if helping at all, with that. And in my experience, that's where I struggle the most. Like that's where the most time is spent, is like to be able to fail and be able to recover and manage the state and pick up the state. That's your persistent state, like your files, your database, your caches, cache invalidation. These are the hard problems, and they stay same problems even with the streaming world.
Well, caching is kind of interesting in the sense, the application we're working on right now at work, we, you know, the fewer caches you have, the more meaningful they are. And in most kind of API design worlds where you're working on, you know, JSON responses mostly over REST calls or similar, a pattern I found that's effective is to just have a fronting cache, an edge cache, and everything behind it should just be, you know, almost no caching at all. Should just know that if this edge cache was invalidated, it should just go all the way to the source of truth and find a new, find the most recent version of the data. And a common pattern I've seen is to have some kind of robust database like CockroachDB, and then on top of that to have a persistent message broker, usually something like Kafka or Kinesis. And then on top of that, to build your applications as consumers of that message broker. And then your applications are constantly, you know, they're able to either, if your clients need push, they're able to subscribe and push. And if your clients need current state, they're able to grab it also from Kafka and respond with it. And it kind of offloads a lot of the true, real complexity of all of the state management, failover, cache, refresh, all of that stuff onto these technologies, which, you know, they have more man hours than any organization that I know of in them.
I think we jumped a few hops. So one of the large issues is if you can allow for lost connections and lost data. That's why I started from Kafka, even though there are tons of questions to Kafka. Kafka is persistent and replayable. So even if each message either did or did not get into the queue, into the channel, and even if your application crashes, you can design it such that you process each message once and only once. And if you fail somewhere, you restart from the same place. Let's not go into lost messages yet, because it's really a huge pain. I mean, ideally, if you can design your application such that lost messages are no big deal, that's best. If it's financial transactions, it's a whole different story. Let's not go there yet. Let's try to pretend we still are almost in the Unix pipes realm. So subscriptions and channels would just simply be, if your data is one record per line, I love this format, one JSON per line. You can just subscribe to it. I mean, honestly, 7 or 8 years ago, I had a design where the whole data crunching framework was SSH, my server, space command, pipe, something. And this something is tool that consumes one JSON per line and does something. This works. So let's pretend we're still there. Kinesis or Kafka just make sure you don't have to parse those JSONs and your callback is called the way it should be called. Forget filtering too. Imagine you have multiple machines doing tail minus f pipe grep, and you only get what you need to get. The state question still persists. I think a lot of people can easily grasp their head around the idea that they can wrap their head around the idea that I have a bunch of streams to consume, and I can serve them. I can produce resulting responses. But eventually, you're going to get you have to go to cache, you have to go to Redis, or you have to talk to a different service. And it's so tempting to write a synchronous call. If it's your authorization service, the call is synchronous. Ideally, if it's a client-side token, it's done locally. If it requires validation against a database, it's a really quick round trip call because it's within the data center. And then suddenly you're told that, hey, you know what? Even if it's a quick call, if it's a remote call, you have to make it asynchronous, and everything breaks. You have to rethink your design pattern. I'm trying to not scare people away from this because it's obviously the future. But the real challenge is not that the data formats are not exactly precise. I mean, everybody who works in this field, whom I know, loves strong typing, and we all get there eventually, I think, if you work with data. But these are constant time problems. Issues with type systems can cost you a day of debugging where the compiler could have caught it in a minute, but it's still a constant. There is only so many minutes in a day. If your design becomes unmaintainable, unless except by a few people who wrote it because it's so hairy and interconnected and intertwined, that's an issue for the company, right? That's an issue for an architect. That's poor architecture if only select few people can maintain the design. So how do we make sure those systems are, on the one hand, reactively streamed, and on the other hand, maintainable?
It's an interesting question. In my experience, I've found that all of these systems, if they're written according to just the standard practices of the RX kind of world, they're maintainable by anyone kind of who's already gone through the journey, who's already understood, that this is just a series of operation on streams, and who understands like that, if you've hacked in some kind of RPC call synchronously somewhere, they'll understand that that's wrong and it needs to be refactored at some point. It's the people who haven't gone on the journey yet, and there are people, who've spent decades without really having to, and that's okay. People who are just used to writing classes and RPC calls and blocking IO, and have been happy to for a long time. And there's a certain kind of resistance to, it's the same kind of resistance really that those similar sorts of folks face, or provide whenever they're asked to do more functional programming in general. It's, well, classes work for me. Polymorphism and inheritance are patterns. They work fine. Why do I need to learn all of this functional garbage? And
there's a big counter argument here, by the way. When people start speaking in this language, I always tell them that OOP was not invented this way. The original OOP is Smalltalk and Objective-C. When objects talk to each other, we are effectively message queues, and the messages are routed by the system. So OOP are not classes. OOP are effectively reactive streaming back from the 80s. We just forgot that.
Yeah, but I guess people get used to their classes and their class factories and their factory factories and so on and so forth. And it's, if you're trying to write code that's going to be maintained by the factory people, it's going to be an uphill battle to do anything besides FactoryFactory. So I don't really know of a good answer to that question besides hire people who are understanding more than one pattern and who are willing to learn new patterns as they emerge. That's much more of a engineering culture sort of thing, which is also, by the way, a key component of architecture as a whole, I think.
I was kind of tempted to ask this when you were speaking a minute ago, so now is a good time. How far off would I be if I just rephrase what you're saying in the following manner? The best way to actually move the world towards reactive streaming is to not be shy to hire people who have never heard of it and just give them a crash course, a boot camp that, you know what, you can no longer call synchronous methods. Get used to that and hope they get red pilled within the first 2 weeks in a company. Would that be an accurate strategy of your recommendation?
That kind of works. I mean, to me, it's always that if you show a person that you can write 10 lines instead of 200 and they don't like it, then that's the wrong person. If you show them that you can write 10 lines instead of 200 and they're all over it, even if they've never seen it before, then they're more like the right person. So hire the kind that are interested. And they'll figure it out. People are clever. It's a lot harder to find motivated people than clever ones.
I used to love the argument about the length of code. I'm slightly more hesitant to use it these days because it often, let's put it this way, it highlights the wrong things. There are so many ways to make the code cleaner, to make the code shorter. And there are so many ways to make the code look shorter and look crisper that are actually ugly and unmaintainable. So you got to be careful claiming that, hey, look, it used to be 200 lines, now it's 5 lines, so this is better. For example, simply introducing types oftentimes gives you a higher gain per line of code. And then if you speak with hardcore Python people who think types are evil and their unit tests would catch that, they would say that it's a good thing that you can just say if X, and you don't care if X is a boolean that's false, or nullable that is null, or an empty array. And so just the cleanliness of code is a two-edged sword. I think, you know what, maybe you can come up with a bunch of examples where the shortness of code once it's re-implemented in reactive way actually highlights the beauty of the very reactiveness, not just the beauty of the toolchain.
I think it highlights more like the truth of what's actually happening, the truth of the fact that our applications are operating, as I said, in an arrow of time, and that they are continually ingesting new information and they are continually producing new output. I think that's kind of what is highlighted by these implementation patterns. And, you know, with regards to the ifx people, I think that even the TypeScript people would agree with the Python people to a certain degree. And, you know, depending on the runtime, I think the right tool for the right job, if you're writing, you know, fighter airplane code or bank server code, then probably you want a more strict type checking system than if you're writing, you know, a website or a blog. But the, you know, the underlying point is that whenever you can save developers time, whether that's because you have a type checker that is catching classes of errors, or if you're writing Rust, then you have a borrow checker, which is catching even more classes of errors, or because you have a reactive streaming paradigm, which is catching another class of errors, which are errors that happen, you know, over time, something where you have an inappropriate mutation of your state because of some input that is coming into your application. It's a lot easier to catch if everything is kind of going into one pipe and branching into or out of that pipe with a, you know, kind of type check system. It's a lot easier once you've made the leap. It's a lot easier to reason about what's going on without having to dig into like call stacks of like, well, why did this get called, or why did that get called? Where did this come from? And your whole application is kind of stitched together in a much more proprietary way that's a lot harder to learn. Whereas if you just take the guys who know how to do reactive streaming and give them this, conventionally implemented application, they'll just say, okay, well, which stage of your stream is this failing on? And they'll immediately be able to see, well, is the input correct? Okay, is the output correct? Okay, maybe not. And let's debug exactly here. And it's a lot, the value of knowing where to put that first breakpoint is quite high, I think. We're talking about maintainability.
You're touching very close to what Anton suggested, and I think I would agree with him here. This callback hell in terms of the callback stack being undebuggable, it's not a bug, it's a feature. It's a feature of the fact that we're trying to run functional Lambda calculus code on a von Neumann designed processors. So, like, in a way, I would say that the win of thinking reactively, if only it was the ease of debugging without this callback hell, without huge code stacks, if only that was the win, it was already a huge enough win. Forget full functionality, forget stateless, use mutexes. Just know that instead of having to figure out what was called from where, you only have to think about a particular mutation that landed in the wrong state.
Exactly. A lot of the tools, like with replayability, the debugging is, orders of magnitude easier as well, because you can replay your state until you've hit the point where something went wrong, and you can see, oh, which operation was this? For in the client world with Redux, this is huge for us, because we can just say, oh, which action, which mutation of the core store, which resulted in the wrong user interface being derived from that state. And you can just go back in steps until you see, oh, this is this action, and you know exactly what to fix. And it's way easier than trying to step through and debug and figure out. It's just miles ahead. And I admit that a lot of people don't grasp it. A lot of the junior and intermediate engineers who are working on the application, they have a hard time kind of just realizing that, hey, you just have to go to this place and find the source of the broken state, and then you'll know what to fix. And they're still, they're used to it. And that's what I was kind of saying earlier about, it's a lot easier to teach someone from new than to reteach them something. So they're used to just going into their objects and functions and trying to figure out on the call stack what's going wrong and who called what. And that's a lot harder to do when you have, like we're saying, with all this, these libraries and all this stuff. It's a lot easier to just look at the, series of mutations of the state, understanding that your whole application is derived from the state. Just look at where the mutation went wrong and what the input was, and was it the input or the output? So it's yeah.
Yeah, it's funny that many years ago we wrote this concept based on streaming one JSON per line, and then I'm a C++ guy, so naturally I hate dangling pointers and stuff. And then some 6 years ago we hacked up some piece called WaitableAtomic. It's like a mutex wrapped into an object that also has a condition variable. So you can only modify this object within some lambda. It's guaranteed exclusive access, but you can also wait on the change on this object. So the clients can say, hey, you know what, I'm going to wait until this predicate on this object, on this data element becomes true. And then suddenly you realize that you've just reinvented the right primitive. I think C++20 has it implemented exactly the way we did. Let's make a small, not really a detour, but let's steer the conversation towards lower level things. Lower level as in down to earth, how to write code. What often bugs me is when we try to teach people to not think in terms of synchronous calls, but rather in terms of state transitions, they discover futures and promises, and they discover them in a way that, oh, you just say yield return instead of return, and then you don't forget to put yield You just make sure you put yield everywhere, and suddenly it actually works. So I mean, it's awesome. It works, but it doesn't really help making sure people follow through what's going on. Is there a solution here?
I think on the server side, like we were touching with Lambda, like there are certain services, like if you just say you can only use AWS Lambda and S3 for your services and Kinesis, to go into the AWS world, then you pretty much have to write correct code, according to best practices. Anything else is quite hard to do. It just won't work properly, and you're relying on this whole, monstrous Amazon infrastructure to make sure that your lambdas are instantiated correctly and called correctly and kept warm for the right amount of time and so forth.
Let's pause here. I think we need to tell people that lambdas can mean different things. There's Amazon Lambda, there's Lambda in Java, and there's Lambda in Lambda calculus. Maybe talk a bit more about that.
Well, I guess, yeah, they're all kind of variations on the same theme, I guess, of your core concept is a function, and it's functional programming. Your core concept is a function that takes inputs and provides outputs. And whatever, pure functions being those that don't access or transform global state, don't transform their arguments, and are predictable, repeatable in the sense that they always return the same value given the same inputs. Those are the building blocks of your entire application. You have no other tools. And once kind of people get their heads around that, and it's hard, like you're saying, real world, down to earth programming. I mean, like with no oversight, trying to transition someone out of static calls and into state transformations is hard. And the longer a person has spent, writing the former kind of code, the longer they're going to have to spend relearning essentially the new paradigm. But it's quite clear that most reasonable engineers, I think, when they see something like, oh, look, I can write a web service in 10 lines of code and AWS will just stand it up for me and everything will just work, they're bought in, and anyone who, spends any amount of time worrying about how long it takes engineers to do things is quite happy when they realize that there's a whole class of things that engineers no longer have to do when they use these kinds of services.
Let me try another angle from which people get introduced to this idea. If you have to work with a database, imagine you cannot have any local state except the database, which is kind of true on iPhone because you have to use SQLite via the local storage wrapper or whatnot. So if you can only have your state in a database, then you can only mutate it with transactions. In fact, you can only get it with transactions. This is a kind of simple concept to grasp, and you can easily sell it to people that, hey, if your application crashes, you gotta make sure that it leaves the database in a consistent state. And ideally, if you have 3 transactions, one after another, be sure you don't leave anything hanging if you crash between them. But then get operations are also transactions. And if you need certain pieces of data to be consistent with one another, you have to get them in a single transaction. I'm trying to get back to the idea of lambdas. So in this particular case, I guess we would all agree that not a mathematical lambda, but I'm trying to be down to earth here. So AWS friendly lambda would be the one that is split into 2. One is called before the database transaction. One is called as a callback after the database has sent you the data back. And ideally, if you can split your business logic into these 2, you've got more than half of what it takes to get to reactive streaming mindset.
Well, and more generally, it's an encouraged pattern to split your read and write logic to be totally independent of each other as much as possible. So yeah, I mean, that's the best practice world, or best practice rather, outside of the reactive kind of world. Even if you're writing purely RPC, RPC style applications, you still want your read data access layer separate from your write data access layer for a whole host of. Go ahead, Dima.
I was about to add that it's true unless you're in super high performance world where you're gonna be making use of tons of test and sets, atomic swaps, which technically are the way to combine reads and writes.
At which point you can no longer rely on intermediate or junior engineers to maintain your code.
Well, yes and no. I mean, yes, if you have to write it effectively, you would much rather hire people who know this. But on the other hand, I think it's one of the best indicators that a technology is mature, that you don't have this constraint on only hiring those who are experts there.
Well, whenever you're doing it cutting edge, whenever you have to bleed the last microns of performance out of a system for whatever reason, whether you're writing a video game engine or a stock trading platform or any other kind of thing where the only way for you to be competitive in the landscape, in the marketplace, is to have bleeding edge performance, then you probably have to hire experts. Because there's always ease of coding and performance, right?
I was trying to get back to the ease of coding, all the way down to the down-to-earth approach of juniors writing code. Imagine someone has grasped the idea of, I'm sort of putting on my educator hat again. It's just one of the easiest modes for me right now. So let's try to help those people. Imagine they have grasped async awaits. They don't yet fully understand that what it translates to behind the scenes. It doesn't really matter for them, honestly, if it's green threads or epals or mutexes or whatnot. One thing that is unclear, honestly, it's not unclear to me, I didn't think it through. Does it really put so many limitations on what your business logic can do if you limit yourself to async await kind of semantics? If you only live in the world of promises and you don't really think in terms of reactive streams and actors, reactors?
Well, I don't think the limitations are much more about practices than about, in the common runtimes, they're much more about practices than about hard restrictions of the runtime itself. It's about what starts to look like code smell. Even if you're, let's say, you're fully transitioned to promises, but a lot of people like to we'll just leave this global state here that I can access all of my promises. And we're going to start to accumulate little checks here, flags there, set this flag in this promise, and then access it in that promise. And things start to get kind of hard to follow. And again, you're breaking the functional rules. So those rules are mostly, at least in JavaScript, in Java, and a lot of these places, they're conventional rules. They're not enforced by the compiler. You're allowed global state. The compiler will let you have it, but any code reviewer who's trying to enforce a functional style of programming is going to disapprove of you pulling in global state or mutating global state or setting some kind of external flag or setting some kind of external temporary variable or cache inside of your promise scope. He's going to say, no, don't do that. And in that sense, it does add some limitations.
Well, if this is the level 0 response, and I kind of like it, then we have to admit Rust may have a big future, because it's the only language so far that makes this human-assisted linting of this kind. Rust is the only language that makes it programmatic.
Exactly, and that's why I'm personally a huge fan of the language, even though I haven't had a huge chance to deliver any meaningful large-scale applications in it. it does automatically, like you were saying, everything that I find myself writing in code review, it'll just catch in the compiler. And I love that about it.
Yeah, it's a whole interesting conversation. When I'm reviewing code, I really love working with people whose code is clean to the degree that I find myself not nitpicking, not looking at minor details, but seeing the big picture. So clearly, we would like to use languages and frameworks and paradigms that bring us closer to the world where you just see the meaning of the code. You don't have to worry about all those small lint-ish issues. And in a way, lack of global state and overall functional approach to code is certainly a huge step in this direction. So I guess getting back to the async await questions, I guess the bottom line is you guys don't really miss much if you only use asynchronous paradigms via these primitives, via future promises, asyncs and awaits.
Well, I wouldn't say everything is async. Like the things that are truly asynchronous are asynchronous, but sometimes you're calling a function inside of a scope and that function is synchronous. It just does something else and returns a value, and it doesn't have to be async. So I've seen also a lot of people who are just kind of onboarding to this paradigm. They just write every function is an async function. And your async should kind of end where it needs to. A promise, if we're talking about just promises are supposed to be a representation of something in the future. And if you don't have anything in the future which you're trying to represent, then you don't need an async function.
Well, yes, but I would actually approach it differently. I think you always need an async function unless you can load your CPU 100%. It's pointless to have a square root function that is asynchronous because you're not gaining anything. But if your function can potentially take a lot of time, if the theoretical upper limit on the CPU utilization of the code is 0, because you can't imagine circumstances where you'll be waiting forever to run 2 instructions. It has to be synchronous.
Yeah. I mean, I think most code can really be broken down into a small bite-sized series of operations that might include some business logic, which doesn't have to be asynchronous, and a call to a remote system, which does have to be asynchronous, or to another thread, which does have to be asynchronous.
Yeah, it's really interesting how these worlds converge. When you truly think functional, there is no global state, but the state is what is passed as an argument to the next invocation of the same function. And if you have a complex topology, the same request goes into multiple places, like fans out. Effectively, what happens is you just have to mutate multiple global local-ish states, whereas each mutation is part of the mutation log. And then suddenly you realize these mutation logs are those time series, time-ordered series of events which do intersect with one another in those small function calls and are all synchronous. Are all synchronized, not synchronous. I'm trying to get to the idea that we haven't really, we use the terms actor reactors. We spoke about the actor model for a while. We haven't really introduced the term. Shall we?
Yeah, sure. I guess my basic understanding of actor reactor model is that your entire program is broken down into a series of, they call them actors, or small programs that execute synchronous logic of some sort. And whatever they're doing, they're going to be blocking, they're going to be waiting for to complete their operation. And all of those agents can only communicate, those actors can only communicate via message passing. So of the 2 kinds of multi-threaded communication models, one being message passing and one being memory sharing, actor-reactor prohibits memory sharing and enforces the idea of threads or actors communicating via messages, and it encourages them to be simple and small and as much as possible just essentially looking like stream transformers, essentially looking like taking some message and as a response to that message, either doing some remote operation or sending a message to another area of the system or any combination of the above.
Well, okay, thanks.
Not
I
sure
like
if
it. Oh, I actually think you have this talent of explaining things from deep inside, which sounds plausible and enlightening. Well, since this is kind of turning into interviewing you, there's one more topic we will not cover today, but I think it will be interesting for one of the future conversations. It's how to split a monolith into microservices. So we're not going there right now, but we have to talk about, you have multiple lectures, multiple stream processes, if you wish. If it's multiple services talking to one another via gRPC or gets and posts, it's usually simple to support multiple API versions. There are standards, there are traditions. You can just have version I and version I plus one, stuff like that. But if you have a service that is successfully and correctly broken down into 25 vectors, and they have intermediate streams which are used to transmit intermediate data, parts of the state from one submodule, from one actor to another. Well, first of all, if you're doing active development, hope you're pushing code multiple times a day. How do you make sure some minor version change, minor glitch doesn't take the whole system down?
Well, this is kind of one of the fundamental differences, I think, between a reactive pattern and an actor-reactor pattern, where, you know, in an actor-reactor system, you really, when you're debugging it, you have to understand how messages propagate through the system. Most of your messages are proprietary. They're based on your business logic. They're based on your business needs. And you have to understand that some incoming external message to your system from a client, you know, it might cause this actor to send this other message to this actor, which sends this other message to this actor. And you have to understand this whole branching pattern of messages in your system. And those messages are proprietary. And it makes it a bit more, you know, when you have complex cases, I think to answer your question, I think, you know, things like Erlang solve it with perfect process isolation and actor isolation, where if an actor fails, it just fails. And if a message isn't received, it's not received. And if the sending actor has a problem because he hasn't received a reply, then he can decide what to do about it. But, and that's why I think, you know, our reactive streaming is, you know, I see it as an evolution because it takes the full scope of all the operations that you might want to do, and it effectively just categorizes them into generic operation types or patterns. You know, are you taking inputs from multiple streams and outputting a single stream? Are you filtering a stream? Are you mapping over a stream? Are you, and these kinds of generic actions that you can perform, within those you implement your business logic. Whereas with the actor-reactor system, you're kind of, it's left up to you, like this, whatever message, get user account details. It's up to you what that means and what kind of operations it represents, and whether you're combining that, you know, how many data sources you're combining and where that's all coming from. It's a bit, you know, the ability for it to kind of sprawl out is a lot more than if you have a system where you clearly know where your data streams are coming from because they have a generic language with which they're described.
Well, yeah, this is just hitting the nail. I'm a huge fan of cleaner code in terms of making sure the toolkit help us, but honestly, sometimes I'm so afraid of hidden complexity. And proper reactive implementations oftentimes are really good at hiding exactly this. You don't fully know which chain of messages can emerge here and there, and then suddenly the old timers are super valuable for a project because they have this sacred knowledge that certain kind of database error plus second level hash hit can have this weird kind of message here and there that suddenly is broken in this version and only noticed 10 versions later. So, I mean, honestly, even though I'm a huge fan of clean code, sometimes I would say that a huge switch statement on multiple possible states and their transitions could even be a better implementation because it's uglier in a way, but it's beautiful because it shows you right away which transitions could you have possibly missed. So if you have like 3 processes with 3 states each, sometimes a Cartesian product of 27 possible changes would actually not be a bad idea. Speaking of different
2,000 lines of switch as your system grows, though, don't you?
Well, yes and no. It's a question of how do I avoid copy paste within those switch statements. If I use C++ and I have like an array of strategies which I populate within cases or in groups of cases, and I know that if certain strategy was added to this array, this destructor is going to be called towards the end. It's still ugly, but it's at least understandable. I mean, the beauty of the flip side of the coin of this beautiful idea that functions have no side effects is that you have to know exactly what can possibly happen behind the scenes. Computers are cruel; they wouldn't tell you if there's one line. I mean, that's exactly why Linus Torvalds hates C++. I'm not agreeing with him here, but I think he has a point. He hates C++ because you cannot possibly imagine there's no upper bound on the number of operations a single line of code would have in the least predictable place. Right. Since we did get to this multiple calls emerging here and there, let's maybe talk about message brokers and queues and how they play into this. So we spoke about kinesis. We spoke about Kafka, of course. These two are not exhaustive. Oftentimes you would use Rabbit or something. When, how, when not to, common pitfalls.
I mean, I think I said earlier that I think a decent, like, generic design pattern that you start off from and that will work for something where real-time persistence and atomicity of something like financial transactions is important is to start with a database that can guarantee you transactional operations, and on top of it put a message broker of some sort that you can use to be notified of changes to the database without having to write a bunch of effectively replication code or a custom replication stream or anything like that. Where if you can just wire together a database and a message broker and have your read data access layer, which is eventually consistent in most cases, have it just read from the message broker, then you will probably be in a pretty good place. So far as what a good use case for Rabbit versus Kafka is, I'm not really an expert here, but generally I found that if you need some kind of persistence, then you can't use Rabbit. And if you need and if you do need persistence, then you should probably use Kafka. And if you need replayability, you should probably use Kafka. But Rabbit's good, I guess, for certain guarantees that it makes about messages being read once and only once, and being able to pick up a message from a queue, and also being able to create a queue topology that is quite sophisticated in many ways inside the message broker, although there are some limitations, which I've personally encountered with regards to rebuilding the queue topology. If it happens frequently, it is not sustainable.
Thank you. Well, I do have more questions, but maybe someone else wants to. Hey Max, we're slowly getting into the Q&A part. Yeah.
Q&A. Actually, I can leave a few words about my experience using JavaRX. I had a project, actually, that one didn't has any persistent. It was like a proxy system, but for the first few weeks, it was a total headache to get to a new paradigm. Like, it sounds, so what was the purpose of the system? Like, we had some request, then we make a bunch parallel requests and like return some data. Yeah, it sounds cool. You can easily make those calls like in parallel, like writing a few lines of code, but actually it also produced a lot of headache mixing different information from different streams. And also, like you were discussing how to manage errors and so on, it also forced you to use some types of pairs of pairs where you have some state and also some object handling errors to be able to get where actually the error was produced and so on. And even for
pairs as in tuples, right?
Yeah, like tuples. So even experienced guys had issues getting that new paradigm, and for sometimes like you had a task, for example, writing it in a more common blocking way, you would spend about a day for it, but due to all those stream and so on, people spend like a week. And yeah, it had benefits because actually that was a high loaded system, and how to say, responsibility of that one was quite good due to streams, but writing it was not quite easy. And so I had a mixed feelings. From one side, it's cool. From other side, it produced a lot of headache.
I'm sure
Maybe
you could.
Got easier for you guys if after a few weeks you kind of started to or if it's something that kind of stuck with the project for its entire life.
Yeah, after a few weeks, okay, you can start writing it faster, but anyway, you are forced to like, so a chain of your flow became like a multiple nested flow. So you do some map, you do some, okay, return some observable, calling another stream, and so on, so on. Then mixing it, it produced some pairs of return statuses and possible errors. Yeah, you start writing it faster, but it's not as easy as in more traditional blocking systems. But how to say, you are forced to, because like system is pretty high load, and in case if you will write it in a more common blocking approach, I don't know, it will, I'm pretty sure that at some state of load it will force you to redesign it, because like your throughput is limited due to this approach. So I think you need to maybe calculate the involvement of developer and the how to say, the cost of that design, because yeah, we as developers argued, oh come on, it's hard to read, understand, and so on, but like a benefit for business was quite valuable because system was pretty high loaded and responsiveness was quite good.
I'm sure you guys would find relief in knowing that they've been trying to solve one of the hardest problems in functional programming, because hierarchical error handling is the easiest introduction to monads, those dreaded monads. So, and if you have to have a Cartesian product of two potential error state accumulating layer by layer and potential data accumulating layer by layer, that's just functional programming at its worst, more or less. So I would even say that you're lucky to have used Java for that, because even if Erlang, for example, could have been a better language, the pain would be quadrupled.
Rust has a decent solution in modern Rust to this problem, where pretty much every async function returns an objective type result, and you can either unwrap it, which will throw, or you can handle the error inside your callback or inside your handling function, and it's kind of your choice. And the syntax is quite concise. say, oh, this thing is unwrap this result, or this thing is this result, but oh, catch the error, handle it here.
Well, but to play devil's advocate, I'm totally with you, but these semantics, these words are a bit too similar to boxing and unboxing, which Java people understand differently. So
Rust also has boxes, which are a bit different too.
I never used Rust, but as I read, it's quite complex to get into that ecosystem. Is it true?
it's a conspiracy. They're making this up so that people are steered away from Rust. You should try it.
Okay.
I mean, honestly, on-board checkers are no different from smart pointers with scope ownership, and a lot of these things just make perfect sense if you wrap your head around why are they introduced, because the main purpose why they were introduced was to give you all the power you could use otherwise, but prevent you from shooting yourself into the foot in the most common ways, at least. It's not as pure as Erlang, but it's totally usable. Although, yeah, no production.
Why do you still use C++, not Rust?
Adoption, legacy. Well, some companies, as you may know, are really. It slowly gets away from the system design topic all the way into team dynamics and corporate structures and management styles. But legacy is not always bad, and you need to be able to build on top of positive legacy. And if the company is C++ for 20 years, I'm the guy pushing for C++ 17 for the record. I think we'll succeed. But yeah, it has implications. All right then. I guess one topic we did not cover. I mean, we did dance around it, but we didn't go all the way in. Is replayability. So imagine you deploy some new version, and some actors are misbehaving. In a perfect world, every message you've sent back and forth is recorded for like 24 hours. So if you found a bug early on, you can in theory replay everything and fix that issue, like full audit, full reconciliation. I don't have experience doing that in production. I mean, I do once, but it was a huge pain, and we ended up doing it all manually, grabbing JSONs, grabbing them again, and then writing C++ to grab them faster. Any experience you guys have? Maybe interesting stories to share?
You make it into message brokers like Kafka and so on?
Well, if all your message brokers remember everything, then in theory you know exactly what message, for each message you know which actor emitted that in response to what input. So if you introduce an error, let's say your balance can be in 64, but you use in 32, and some balance got negative. In theory, you could fix this by just fixing the code and retroactively applying it. You make a fix to your code, and then you pretty much rerun it from the past. That's the pure replayability.
Yeah,
Right,
at our company, I mean, we have a team that maintains a Kafka that can replay every message from the time they stood it up, and their interface is aware of the different versions of the messages over time, and they're able to replay the whole world with their whatever updated code from the beginning of the time they started sampling messages, and they do it routinely. Like many things, if the first time you're doing it is when you have a production problem, it's not going to be fun. But if you make that part of your regular workflow, that, oh, I've created this new feature, let's see how it works on the last 2 months of user data or of activity data from our site. Let's replay the world, and it takes them, and this is a pretty big company, and it takes them a few hours or sometimes overnight of quite a bit of computing time to replay the whole world, because it's a big world, billions and billions of messages. But if you make this a standard practice, I don't see any reason why it has to be painful.
Just wonder, is it a good practice? Actually, I don't have any experience with the messaging systems. Like you said, replaying months of data. So is it a good approach to keep such a huge log?
Keep everything. Metal's cheap.
Cheap.
Hard drives are cheap. Keep everything you can. If you're designing a modern system, persist things, Glacier, whatever, cloud, on-prem, whatever thing you're running. Keep everything you can.
Well, it's cheap, but due some threshold. Like I had experience in one company, so they had like logs for 2 months. Then it was such a huge amount of data they had to put it into like a tape. So yeah, it's cheap, but 2 months is okay. 3 months is okay. Year is okay or no? Then Kafka became like a database with a streaming functionality.
Logs are a bit different. I mean, logs are not really application data, but if you're running a messaging system, any mutations of your application data, that would keep the database operation log in the beginning of time as much as possible.
Yeah, in my experience, logs absolutely no. Mutations to like balances and accounts absolutely yes. And the part where I'm uncertain is the history of lifetimes of auth tokens. So in theory, you would like to know each session of each user just in case you may need to go back and figure out from which device did they do something. In practice, that's a bit too much. So I don't have a good answer, but yeah, I'm a firm believer that today it sounds like a bad idea that you use Kafka as the source of truth. And I think it is a bad idea because Kafka was not designed for that. But as a paradigm, I think it's the future. If you think about it, mutations are the source of truth. Replaying the log up a certain stage, be it yesterday, this second, or 2 years ago, is just a cache. It's this logic of snapshotting is secondary to the logic of keeping the source of truth.
Looks like it's a quite separate topic to talk for a few hours more.
Well, not really. I mean, of all the topics this relates to, this event log as a source of truth, of all the topics it relates to, reactive streaming is probably the closest.
Well, that's just it. That's a stream too, right? Your operations over time, over months, over years to your database is just another stream. And if you can replay that, meaning not use Kafka as a source of truth, but use it as a way to replay operations onto your source of truth, meaning onto your database, then that also becomes an extremely valuable tool that you can essentially forward and reverse time in a deterministic way in your application. And that's not something a lot of applications can do these days, with some exceptions of modern applications who have kind of thought about this from the beginning. But it offers you incredible amounts of power to change things. Like you can rekey your database. You can change columns from the beginning of time. You can do whatever you want. Any kind of, a lot of legacy systems have tech debt that is pretty much impossible to address, in the sense that there's so much data and no way to change from the beginning of time for the purpose of audit. You have, let's say, in some hypothetical company, someone made a stupid decision and decided to key the database by email address. And, let's say 2 years down the road, you realize this is a bad idea for obvious reasons. And you want to change that, but you already have a bunch of reports, a bunch of code that are all written on top of this. How do you do that? You have a bunch of historical data archives. Well, if you have this system of just replaying new code onto existing data and replaying database operations from the beginning of your system's operation, then easy. If you don't, then good luck.
I was just looking through my notes, so I guess we can begin to wrap up. There was one simple example that we didn't cover. It is super obvious. Most of us have used it in practice, but it could be the easiest introduction to reactive streaming. It's the idea of a deferred action. Imagine you need to take some action in the future. Unless you're totally bare metal and you know nothing about your system overall, chances are you have some message queue coming into you. So if you have some action to be performed, let's say 10 seconds from now, most likely you would send yourself a timed message, right? You're not going to spawn a thread and say do A, sleep 10, do B. You would say do A, mutate some internal state that A is being done, and send yourself a message that is going to arrive in 10 seconds, with the message being, hey, look at that result of A and do B. Once you realize timed events are as first-class citizens as the input synchronous-ish requests, life gets easier.
Yeah, and if you have nice async await paradigms, it gets even easier, right? Just await timeout 10 seconds. And I guess that all relies on, whichever runtime you're in, it relies on a scheduler implementation that can handle that can take a message and deliver it in 10 seconds, or that can, wait with your call stack for 10 seconds and put it into the right place and schedule it. So a lot of these things do rely on schedulers, which we take for granted in a lot of these systems.
Yeah, I mean, it's closer to the work of some of us, but if you have a regulator that needs reports, you need to make sure those reports are up to date as of certain moment, whereas some data can come in the future. A better example would be, there was a company building a huge offline product, and after the acquisition, they had KPIs based on their active usage. I will not name the company. But then they realized that since the product is offline, you don't really know the number of active users you had this month until an undetermined amount of time in the future, because there could have been one user who used the product, who used the app, closed it, and opened it again years from now. So you can't just say, hey, as of the 1st of March, we know that in February we had this many millions of active users. And the solution to this is to make sure that you don't measure active users as of the end of month, because you know you're going to have delayed messages. You measure it with a fixed delay, let's say 5 days, 10 days, 20 days, and you extrapolate, because you know that, hey, if you measure within 5 days delay, looks like you catch 95% of those users who actually use the service. And if you look at 2 weeks lag, it's 99%. And then you claim that, hey, I've only seen this many users, but I know it's the real number is higher because of, well, how the service looks like. And to me, it's a perfect example of an actor that is making decisions about the past from the future, right? In order to compute the number of active users in February with a 2 weeks lag, you need to replay the usage logs all the way up to mid-March. Your message receive time is not the same as the message send time. So you look at message send times, cut off there by February only, and then count the number. Perfect example of reproducible log crunching.
Now it's starting to smell like machine learning, isn't it?
Actually, yeah, on a closing note, I do machine learning a lot-ish, and I have experience doing that in production at large scale. Looks like we have enough people who want to talk about this. So hopefully in the next few months, we're going to have episodes. I'm mostly looking forward to people who have this blend of theory and practice, as in, you know, mathematics, but you also grew into people manager, and you know how to decide what to not do because it sounds good in theory and then in practice, and vice versa. Yeah, I have a few friends who are good at that. Hopefully we'll get a chance to speak. Anton? I think your lips were moving.
Let's be more precise on the topic.
We'll take it offline. All right, let me then stop the recording. Thanks everyone.
Can I ask one question, if it's not too late? We didn't really talk about performance and overhead that we have because of those. So in front end, it's not really a big problem. Like with React and Redux, you can store all the state in the world on the client and replay it as you want. But on the back end, I think sometimes you really need to think carefully how to and where to consume your stream. Like you can't really process every message on like thousands of different machines just to serve it to the user. It can be too much overhead or something, and we didn't really touch it. And if you can say a few words about this problem, it would be nice.
Yeah, I guess so far as performance goes, you'd want to look at doing any operation as few times as possible. And if you have, if you have to aggregate something, if you have to transform some stream, it's better to transform it once and then feed it to many outputs, many consumers, than to have the consumers consume a more raw stream and do the transformation each individually themselves. Because of course your transformation can be cached and your consistency will be eventual. But in that sense that, whenever you're looking at your overall system design and you look at which operations are taking place where, if you're finding that you're having a lot of systems which, because of shared code or because of happenstance are effectively doing the same operation and they're doing it, consuming a more low-level stream, then it's a good candidate to move that operation to a higher level and consume already the output. I don't know if that's a satisfactory answer. Also on performance, note that a lot of implementations actually, like especially in Java, like Maxime was saying, are enable faster performance because the threads themselves aren't blocked, and the application, because of the scheduler, is able to actually handle a lot more input without doing things like exhausting a thread pool. So there are two sides of that kind of coin.
Yeah, I would add, you gave a super high level and super low level answer. I think what Maxim was hitting at is more the middle one, as in how do you shard the data? How do you make sure the right subset of machines get cache locality, which is exactly the painful part, right? Because it's where theory meets practice. On the one hand, you'd like it to be as replayable, as reproducible, and as clean as possible. On the other hand, you don't want the actual server that was up and running in the past to be part of the reproduction in the future. So yeah, there are some leaky abstractions to work around.
Well, those are problems in a general case that need specific often solutions. But generally, yeah, the pattern of avoiding caches as much as possible outside of edge caching is kind of a decent one to follow in the general case. Notably, you can't always edge cache like user specific data, but public data you can often get away with, like edge caching responses and states, especially over HTTP. They're very performant ways to do that.
I'll give an opportunity to show off a bit. I once built a prototype for the product that was designed as the blockchain killer, cryptocurrency killer.
I have to drop. Thank you for the nice conversation. See you.
Yeah, thanks a bunch. See you soon. So what happened? Well, basically, imagine you have to build a blockchain, but you don't need to adjust for Byzantine consensus. So you're not being hacked on a protocol level. So it turns out that that's actually part of the design I always use. I used it in the design of the chat service. When you have proxies that convert a bunch of independent JSON each requests, they just pack them into a tight binary format and stream them to the machine that does the job. And if you can afford to do it, performance-wise, you win a lot, because one of the things actor model wins you is isolation, because everything is done sequentially, not concurrently. So it's in a simple words, actor model means single thread. But if single thread in most cases means login, mute access or whatnot, in case of super fast streaming, single thread means there's some other thread that receives from network or whatnot, prepares your data stream in memory and then moves atomic pointers, and then your actual thread is operating at 99.something% capacity because it just always has this buffer of the actual tasks to execute upon. So in my example, the actual task was just moving money from account A to account B, respecting certain checks by some logic. And realistically, the only bottleneck was just this thread. So you could shard things effectively. And in order to achieve the number that was 100 million TPS, transactions per second, we've hit that easily. And in order to achieve this, you actually, not only you lose by using actor model, by using reactive streaming, you have to design around the idea that your actual executor, your actual business logic is run as the single solidified reactive stream consumer that produces the other stream. I think in my case, I even did a deeper trick. I made sure that the binary format of the request had a placeholder for response. So I had like a buffer. My service runs through it in one thread and stamps those results. And the other thread just looks at the atomic pointer of up to where is it stamped, up to where is the circle buffer already full of results, and sends those via network in large enough packets. That's how you get more than 1 gig per second CPU utilization performance on your input data flow. So if you want to do things super fast and they are all tightly interconnected, so they don't scale horizontally well, XR model is pretty much your only way to get there, which is effectively reactive streaming on steroids.
Yeah, it's a somewhat business logic aware or message format aware scheduler implementation that does that, and that's what all these systems rely on is some kind of scheduler, and a lot of your performance is tied into how effective that scheduler is.
Yeah, let's hope we live long enough to see the next generation of CPUs, GPUs, or whatever else PUs optimized for these kind of tasks. So we can write readable code and have it executed the way it should. I mean, really, we hypothesized about this. Let's hope it's a closing note. Or Maxim, do you have more things to ask? We hypothesized about this many years ago, and it's finally happening. Imagine the fluid agile CPU based on FPGA. So there's no notion of like 16 cores or 64 cores. Then there's no distinction between CPU and GPU. For certain kind of computational task, it can rearrange itself like a T1000 Terminator killer. It can rearrange itself into 10,000 cores, and suddenly it's a GPU. And then it's a system on a chip topology that performs tricky tasks that would be super slow if it's a CPU instructions conveyor, and suddenly it performs a year worth of work on a single computer within a few hours. I'm almost positive we're going to see something like this sometime soon. I think it's right now mostly about the number of times you can rewire the chip before it goes bust, and the power case.
Just saying, M1 is starting to look a lot like the architecture you're describing, Apple M1.
I would sure hope so, yeah. I mean, it's this Harvard, it's still Harvard architecture because large parts of that are hardwired to be either CPU or GPU, but yeah, we're getting there. Thank you, Fox. Let's call it a day.